Hi, this is Dr. Tagwa, the Chair of Computer Science Department at the University of Nevada, Las Vegas.
Hello everybody, my name is Dr. Fonseca
And I would like to invite you to watch
OCR post-processing using support vector machines. OCR stands for Optical Character Recognition, and it's the idea of taking text and scanning it, converting the black and white image of text in a 2D coordinate of little pixels. And so when you're doing that math, you go ahead and create your OCR text. Now, there are going to be some OCR generated errors. This is a typical error because from an OCR standpoint of view, the R and the H look very similar. That stage where we are fixing those errors is considered to be the post-processing stage, where we're trying to improve text that has already gone through the process of OCR and we no longer have the original text. In a way, it's the equivalent of somebody proofreading to find more errors. What I'm going to do is I'm going to first talk to you about the features that I'm using. I'm going to talk to you about attempting logistic regression, how that didn't work out very well, and then we threw SVMs, which is going to be the main focus. And then I'm going to briefly talk about things to improve the results from the SVM, which are, normalizing your data sets and balancing classes, which are pretty standard things you can do. In this case, we are working in supervised machine learning. What we have is a list of candidate words that we've generated with the previous research, and now we're trying to decide, is the candidate a good one or not? So here's the really cool thing about SVMs versus something like log regression. We all know we can apply the Kernel Trick to lift the feature space into a higher dimension, where we can actually achieve non-linear classification, because in the higher dimension, we have the ability to linearly separate the data with a hyperplane. You have all these different kernel functions, and polynomial is the one that we mostly focus on, but we want to try RBF later on. I have a video on SVMs on my YouTube channel, so you can check it out. We're trying to correct misspellings, right? OCR generated errors. And so one of the important things that we want to do is, how close is the word that is wrong with the correct word going to be? And that's our Levenshtein edit distance. The wrong word into the potential candidate. What do we have to change? What do we have to insert? Or what do we have to delete? And so that's a very useful value for us, because the smaller the number, the more similar. Of course, two words that are identical have distance of 0. So that's going to be the first feature that we're going to keep track of. Next, we're going to keep track of the confusion matrix. So the confusion matrix is going to maintain that record of what is a popular error that you make with OCR. For example, L to I. You can see how it's very easy for a scanner to misrepresent an L into an I, because maybe it sees a little dirt or it doesn't read the straight line, or vice versa too. The dot from the I might be so close to the stick of the I that it just combines them and things like that. So anyways, that's going to be the confusion matrix, which is basically how popular is a incorrect substitution, insertion, or deletion. Let me talk to you about what unigram backwards and forwards are. Unigram frequency is how popular is our word, and by that I'm saying how popular is the candidate. Is our candidate word a very rare word to see, or is it something like da, where it's super popular? Because in that case, we're gonna play a little game of statistics and say that if given the choice between 10 words and one of them is a super popular word, the odds are that most of the time it's gonna be the super popular word, the correct candidate. We're just saying that's going to be one of our potential features, is how popular a word is. And then backwards and forwards bigram frequencies, we have word 1, word 2, and word 3. Word 2 is the one with the error. So what we do is we look at word 1 and word 3. We can see how popular word 1 is and word 2 as a pair of words. Whatever has more frequency of that pair is a higher chance of being the right candidate. And so we do that with the word before and the word after. In this case, we are using Trek 5, which is an OCR dataset where it has the originals dataset and it has a 5% character degraded dataset. Let me walk you to the second line. 1, 918, 82, 82, 0, and 1. That means that the word register to register, which is our candidate that we're suggesting, the edit distance is of 1 because all we replace is H to R. The frequency of that H to R replacement is 918. The unigram frequency of how often register appears in a corpus is going to be 83. The backwards bigram frequency and the forward bigram frequency are in the specific case of the phrase that has the misspelling. If the misspelled word is register, we look at the word before and check how many times a candidate combination appeared in the training corpus. Similarly, for the forward, how many times does that pair follow? So if the error phrase happens to be federal register is, we would look at the two pairs, federal register and register is. So anyways, the idea is you generate the data set like this, and so now it's just a list of numbers. So we generate a candidate, and what you can see here is that we have 14,000 correct candidates and 310,000 incorrect candidates. there's an imbalance that we're going to talk about later. So we threw in logistic regression just to test it out, 92% accuracy, but this was just on the training set itself. That's of course useless. If we go ahead and try training and test set as you properly should do things, when you want to do train, test, and validation, but in this case we're just experimenting, so we did train and test, accuracy drops down to a 4%. What does that mean? It was trying to overfit with the first case. It was practically useless. That's why we go into libSPM, which is an implementation of support vector machines. And in this case, we did Polynomial Kernel. In this case, we still kept a 93% accuracy. That's much better than 4%. Our precision is 85, which is pretty good, but our recall is 10%, which is pretty bad. When you have high precision, it means that there's very few false positives. When you have high recall, it means that there's very few false negatives. False positive is accepting a wrong word. A false negative is not accepting a correct word. What the recall is really telling us that it's low is that we're not accepting words that we should. What do? Well, the two most basic things, 101 machine learning that you can do is you can try normalizing your data set and balancing your class distribution. So why do we want to normalize our data set? Well, as you can see, our values vary very greatly. The confusion weight especially can go very, very high. Those are big numbers. And the other ones like frequency of unigram and bigram are not as high. And edit distance is super small. Typically, where 4 is too much. So what can we do? Well, we can rescale the data using Z-score standardization. Or the other one, I find this really cool picture on the internet, min-max is actually going to be the best thing. What is min-max? It's making your data from a range of 0 and 1. So you take the biggest value of the data, you take the smallest value of the data, and those are going to be your min and max per se, your 0 and 1. And you fit the data, everything in between. And so here's an example of what the data looked like before and what it looks like now after it's been normalized. Of course, when we try normalization, we achieve much better results. We can see that the accuracy is 96% and precision and recall especially is a lot higher. So this is actually going to be one of the best things as well. But this is just training. So let's go ahead and training and test. With training and test, it actually performed relatively better, which is interesting. We have precision 91% and recall 58%. And this took 6 minutes and a half to run versus hours with the normal data set without normalizing it. And it took 130,000 iterations. And it generalized well with that accuracy, 96%. Slightly higher than the training one, actually. There's a little bit of more false positives than the original data set that was not normalized. However, the precision went up because we had more true positives, which means more successful corrections. In this case, we actually had before 494 corrections, and now we had almost 3,000 corrections, 2,600. So that's pretty good. And the increase in recall that increased to 58% from 10% means that false negatives decrease from about 4,000 to under 2,000, which means that less incorrect words are accepted. So overall, normalization was a huge success, and that can be seen in our F-score that went up dramatically from 0.19 to 0.71. That's very, very good. We now have successfully corrected 58% of the errors. Finally, let's talk about over and undersampling. So again, we have that big imbalanced data set. It's actually 4.5% is only belonging to class 1. So what is oversampling and undersampling? That's when you artificially increase one class of the data set so that you can have it balanced. So instead of having 13,000 of one data set and 400,000 of another data set, you extrapolate your data or do other things to it, to interpolate or whatever, to create more points out of nowhere, really, which can cause other problems, but ultimately to try to balance it. And so you can see here that kind of happening as you can see from the top, which is the original data, and then the different oversamplings using A-design, SMOTE, or random. As you can see, it sort of increases the concentration of points. Like the purple points grow a lot more than the original data set, which helps the data set to balance itself. And so we use SMOTE in our case. We lowered our accuracy a little bit to 91%, but our recall went up very dramatically to 91%. And that's the highest that we've had so far. Before it was 58%, so as a comparison. And the accuracy went down from 96 to 91%. And overall, because of that, the F-score went down from 71 to 59. So I would say that the imbalance model is the clear winner. However, you can apply ensemble learning to learn from both the balanced version of the dataset and then the imbalanced version. And you can use both because the recall is, I believe, the highest that we've seen. And so that's a good thing. As you can see here, our false negatives are pretty low. And so that pretty much draws it to an end. As I was saying, I wanted to talk about what kind of errors we had. And so ultimately, the two kind of errors that we have are false positives and false negatives. And so what can we do? Well, you know, in this case, one of the issues that we're having is we need to do a little bit more cleaning of our data set to avoid this kind of errors, and to use some stemming potentially or things like that, because it can miss words because they're very similar in the heart of the word, but maybe they have a punctuation or capitalization or other things. So, you know, ideally, there's a lot of things that we can do. And so to summarize, you know, we created our candidates and we normalized the data set. I showed you how to normalize, balance it. And in the future, we want to create more features. Like I said, do some stemming and things like that, do some assembly learning. Overall, I would say that our precision and recall are acceptable. And again, think about the positive here, that we're correcting words without creating more problems than we're solving. And yet again, we don't, I mean, even though we say we accept or reject a candidate, we can still, you know, if we can still feed this as a suggestion to a final end user, you know, and then have him make the final choice. So ultimately, this doesn't have to be a perfect score. A perfect score is practically impossible. Most people that say they have such a high F score or precision recall are making it up and they don't have the data to prove it. Ultimately, we want to do the best we can while not having to just work for our very specific data set. And so that's going to conclude our presentations and about our paper. If you would like to find out more, you can always come check out UNLV on the website, and you can contact me and I can give you some information, check out the source code and things like that. And I thank you for your time. I hope that you have a wonderful day, and thanks again.
Thank you.